And so the rules being that there has to be two terms. Right? There has to be subtraction between them. And then both terms have to be perfect squares. So I don't know if any of you guys looked at that text I sent last night about getting yourself ready for class and all that list of squaring and cubing and stuff. It's going to be pretty helpful today. What we're doing is to know what squares are, what up through 15, and what your cubes are up through 10. Okay, that you're able to recognize those numbers. Okay? Can you look at 49 and say, oh yeah, that's 7 squared? Can you look at 144 and say, oh yeah, that's 12 squared? Okay, start recognizing those numbers for what they are as being perfect squares. So if a problem meets these criteria, we can do this in a faster way. Okay, so are there two terms? Is there subtraction between them? And then are both terms perfect squares? Okay, so as I look at this first problem, two terms, obviously, there's subtraction between them. And then is 9x squared something times itself, right? What would I multiply by itself to get 9x squared? Is 25 something times itself? What would I multiply to get by itself to get 25? If it checks all those boxes, which this does, what we can do to factor it very, very quickly. All right, think about what factoring looks like when we're done. It's two sets of parentheses. Again, this is just a shortcut on the AC method. Two sets of parentheses. There's always a plus and a minus, because that's the only way to get a negative here. You have a positive times a negative. And then after that, all I have to do is say, what multiplies to be 9x squared? All right, what times itself is 9x squared? Yep, right, Kyle, 3x. And what times itself is 25? Yep, right in, 5. And so I take that 3x, it goes in the front of each term, or a binomial, and then I take that 5, and it goes in the end of each binomial. And I'm done. Okay. So, just how do we know we're done, right? Nothing in common, nothing in common, no more squares or cubes or anything like that, right? The same questions I've been asking you guys. How do you know when you're done? And quickly checking, does it work? 3x times 3x is 9x squared. 3x times that would be negative 15. 5 times 3x would be positive 15, so those would cancel. And then 5 times negative 5 would give me negative 25. Right? It all multiplies back together to get where we started. Right? And it was very fast to factor. I love difference of squares factoring. It's so fast. But you have to recognize it. When you see it, you can do it. It's very fast. Right? But you got to see the squares, right? To see the pattern. This is all very pattern based. Okay? And look at the next one. Does it have two terms? Yes. Does it have subtraction? Yes. Are both terms perfect squares? X squared, well, that's x times x. 144, that's 12 times 12. Yep. All right, hits all the boxes. I need two sets of parentheses. I need a plus and a minus. It doesn't matter what order you write them in. Then I say, where did x squared come from? Well, that's x times x. Where did 144 come from? That's 12 times 12. And quickly glance, anything in common? Anything in common? Nope. Any squares or cubes or anything like that? Squares or cubes? Nope. So I'm done. Okay. If it looks like that, you can factor it like this very quickly. Okay. So it's called difference of two squares factoring, or difference of squares factoring is usually, or difference of two perfect squares factoring. I usually just say difference of squares, just to be fast. Okay. I want you guys to try the third one here. Send me what you got in the chat. You all right? Student in person here is already done. The pressure is on. Good job, Aiden. Yep. does take longer to type it out. Here, Kyla. Jake, what you getting? Masons, what you getting? Zoe, what are you getting? Caitlin, what are you getting? Good job, June. Good job, Jarrett. Addison, what you getting? Good job, Keon. Okay. Yeah, 2x plus 7, 2x minus 7. Again, it does not matter which one you have first. I can take those two groups and switch them. That doesn't matter. I can't take what's inside and do anything with it. Okay, but the two groups can be moved. Okay. So what about this last one here? Does it check our boxes? Does it meet our criteria? Yeah, right, Kyle. It'd be a good thing to put in the public chat. They're not perfect squares, okay? We got two terms, we got subtraction, but they're not perfect squares. Well, what are we forgetting to do? What do I tell you guys to always do first and not do it? What do you mean by that, Aiden? You guys are all set in the private chat. Yeah, there you go, Sam. GCF, okay? So is there a GCF, right? Always look for a GCF first, okay? So do we have a GCF? They're both even, so at the very least, right? You take a 2 out, and then if we take a 2 out, maybe we see more. Okay, who knows? Maybe we start there. 25x squared, 16. All right, you can definitely see that 25 and 16 don't have anything in common. Okay, so sometimes you don't have to worry about finding the GCF. You just find out something, and then maybe the next one will reveal itself. Like, then maybe I see another 2 or something like that, or a 3. Now that the numbers are smaller, it's easier for me to see. Okay, but at this point, we should be able to see that 25 and 16 don't have anything in common. Okay. Well, are we done though? We look inside and say, do they have anything in common? No. Do I have any higher exponents? Yes. Ooh, so I need to think about how can I do this? Or can I do this? No. Can't do grouping. I'm going to try, we can do AC method, but I'm going to try something different because this is only 2 terms. Okay? So perfect squares on both, subtraction. So just like last time, that 2 needs to hang out. If I'm going to do difference of squares factoring, it means I have 2 sets of parentheses, right? And then I have a plus and a minus. Then we say, where did 25x squared come from? 5x times 5x. Where did 16 come from? 4 times 4. Now we go back and look. Anything in common? Nope. Anything in common? Nope. Any higher exponents? Nope, nope. So we should be done factoring. How do we know that our answer makes any sense? Okay. So you can check very quickly to see if it makes some sense. We're not going to check the whole thing to see if it all works out. We can check to see if it makes some sense. 2 times 5x is 10x, times 5x is 50x squared. 2 times 4 is 8, times negative 4 is negative 32. So we can see that we got the front and the back right. There's a really good chance that we also got the middle right. But we know we got the front and the back right. Okay? We don't know that it actually adds up to be 0 in the middle. That's a really good chance. Okay, so we don't have to sit there and check the whole thing. We can check parts of it quickly and see if our answer makes sense. Okay, really common mistake would be like, what's the square root of 16? What do you think someone would say wrong if I said, hey, what's the square root of 16? What would you think a common wrong answer would be? Yeah, 8, right? And you go and check your answer. 2 times 8 is 16 times 8. Is 16 times 8 32? Nope. So we can see that our answer doesn't make any sense. Right? There's no way that's 32. Okay? So And there's a really good chance that if those two pieces work, that the rest of it will also work. Okay? So this is difference of squares factoring. We're going to starting to see more of these problems where you're going to see what I call layers of factoring, guys, where you have to do a GCF and then something else. We've seen those peppered in here and there, like a GCF and then AC method. We're going to start seeing more of it, okay? Especially because difference of squares is so fast factoring, we don't feel like we're bogging you down, making you do it, okay? Because you should be able to do it really quickly. I love difference of squares factoring. It's so fast. You got to see it. Okay? Once you start seeing it, it's like boom, boom, boom. So easy. Okay? Anything about difference of squares you guys want to talk about? Oh, wait, shoot. I have something to talk about. All right, so I'm going to give you guys kind of a warning. Okay? Some of the common mistakes. Okay? So something like if I ask you guys to factor, I don't know, 49 x squared minus 8 or something like that. Okay. So this is not factorable. All right. We have two terms. We have subtraction, but they aren't both perfect squares, right? 49x squared is, but 8 is not. Okay. So that 8 is messing it up. There's actually nothing, even if we tried the AC method, we wouldn't be able to factor that. Okay. There's nothing we could do to find something times something else that would equal that. Okay. That is not factorable. In the same way, something like 16x squared plus 25. This is not factorable. Okay, we got two terms. We have perfect squares, but it's not a difference. Right? Difference means subtraction. This is addition. Okay, a lot of students think that this would be 4x plus 5 times 4x plus 5. If you FOIL that out, you do not get 16x squared plus 25. Right? It does not work. Again, there is nothing that multiplies by something else to give us that besides 1 and that. Okay? There are no factors for that. So it has to be a subtraction in order for that to work. That's the only way to make that middle stuff cancel is for a plus and a minus. Okay, so those are really common mistakes. That's why you guys will see those. Try to avoid them. Okay. Maybe anybody need more time here? So the difference of squares stuff can kind of come from AC method. We've worked with AC method problems enough where we can start to see how the difference of squares things could happen. This next type of factoring is kind of the last thing I want to talk to you guys about as far as factoring goes, is really there's no way for us to find it. Okay. People know that this works because of what I'm about to show you. Like when I taught you guys to factor, I showed you, hey, what if we distribute? Well, how do we undistribute? Right? And then we started distributing more in complex things. We say, how do we tear it apart? We could go back and kind of reverse engineering the distributing to factor. There's really no way to reverse engineer this distribution. We have to notice kind of how these things interact, and that's the only way we're going to be able to pull them apart is by really focusing on the pattern of it. Okay. And so I want to do these two distributions with you guys so we can start to see how the distributions act so that we can try to see back to the pattern. But really, I'm going to have to tell you guys the pattern because it's not that obvious. So, this would have happened, hundreds of years ago where people were working on this stuff, but their jobs were to sit there and study the math for this, like for hours and hours and days. And then they finally saw the pattern. Here, we're going to try to show it to you in 10 minutes. Okay. So factoring is just undistribution. So let's look at the distribution, see how it works, so we can try to pull it apart. Okay, so here we have a binomial times a trinomial. Okay, I'm going to take that x, I'm going to distribute it, which is x cubed plus 2x squared plus 4x. I'm going to take that negative 2 and distribute it. Sorry. So that gives me negative 2x squared minus 4x minus 8. After distribution comes combine like terms. Well, those will cancel. Those will cancel. So that gets us down to x cubed minus 8. So I've seen students struggle in the past with this because, physically this is so large, there's so much written here, and then to multiply it together, usually we get more stuff when we multiply. To see it shrink like that has messed with students' eyes. Okay, but again, it's all because of that canceling that happened there. Okay. What we're going to be after is how do we go this way? Right? I don't want to do that yet. I want to go through another one first to help you guys kind of see it again. Okay? But eventually we want to be able to factor that thing. Right? And these are the factors of this. Right? This times this is this. So these are the factors. Right? That's where we're headed. Let's try it again. Ooh, that's fun. Yeah. So how are these things going to interact? What are we going to end up with? How are we going to be able to pull it back apart? Okay, that's what we're up to here. As we do this distribution, combining like terms, where do we end up? Then how do we take that and go backwards? Okay. So 3x times 9x squared, 3x times 12, negative 12x, 3x times 16. So that gives me 27x cubed minus 36x squared plus 48x. Okay, I'm distributing 4, gives you positive 36x squared minus 48x, and 64 is 4 times 16. So we have like terms to combine. Oh, but we see that they cancel here again. And then these two also cancel. And so we end up with 27x cubed plus 64. Again, we see how everything kind of shrank, right? As far as the number of terms goes. Can, again, sometimes be confusing. Okay. But what I want to talk to you guys about is how do we do this? Right? And this is actually the essential question for today. If I go back to it. All right, how do we factor 27x cubed plus 64? Right. So how do we do that backwards? And so what it comes down to, right? So we can see that it is factorable. Right? There are things that multiply together to be that. That's all based off of a pattern. Okay. And what it comes down to is that there's a special relationship here to here. Right? That 27x cubed is 3x times 3x times 3x. So I'm not square rooting, I'm cube rooting. Right? The cube root of 27x cubed is 3x. And then there's also a special relationship here. That 64 is equal to 4 times 4 times 4. So the cube root of 64 is 4. Okay? And then this sign right here is always going to be the same as that sign here. And will always be the same. Now the pattern there stops. The relationship between this and this stops. Where I look now is the relationship between the rest of what's going on here. So 3x, well, what's 3x times 3x? 9x squared. Okay. What's 4 times 4? 16. Where did 12x come from? Oh, that's just 3x times 4. So that's where that number came from. This is always a positive. And this sign is always the opposite of whatever that is. So these two signs are always the opposites of each other. And those being opposites is what makes those things cancel out. Okay? One of them has to be positive, one has to be negative. It doesn't matter which one. It doesn't matter. It matters a little bit, but one has to be negative, one has to be positive. Okay? That makes all that stuff cancel. So what I want to show you guys is a mnemonic device to help you remember that pattern I was just talking about. Okay? When I was taught this back in high school, the teachers just said, here's the pattern, memorize it. Okay? If you guys go online, you might see that same thing. I know one of the paras that I work with a lot just likes to say, here's the pattern, memorize it. I'm not big on that. I prefer this. Once I learned this mnemonic device from my other teachers, I liked it better, just a different way of remembering. But mnemonic devices are just that, something else you have to remember that helps you remember the thing you're trying to remember, right? That's all it is. Like FOIL, what does FOIL mean? Okay, it stood for something. Back then you had to figure out what it stood for. Or, there's other mnemonic devices you have for other classes to help you remember things. So it's one thing that you remember to help you remember something else, right? By the way, you have to memorize something. What's up, Audrey?
I thought you were going to move on, so I just told you to wait, but you're fine.
Okay. So this mnemonic device is CC stops. Okay, so there's a little space there between the CC and the stops. I think when I first learned it, the teacher told me it was crummy stops, but the crummy doesn't really, it's just the C's that we're after when we say crummy. So I just shortened it to CC stops. Okay. Again, this is a mnemonic device, which means that each of those letters stands for something. Okay. So CC stops. So the C's both stand for cube root. So CC stands for cube root. Now you guys heard me talking about cube rooting just a second ago. The S's both stands for square, not square root, just square. You guys heard me talking about squaring just a second ago. The O stands for opposite. You guys heard me talking about opposite signs a second ago. And the P stands for product. You guys heard me talking about multiplying two things a second ago, right? So CC stops. Cube root, square, opposite, product, square. Okay. I'm going to walk you through a couple examples about how to use CC stops to help you factor. Okay? Again, this is just a method. The other one is purely memorizing the pattern as it's written. Again, I'm just not a big fan of that one anymore. And there's also other different little words and stuff I could use here. Okay. Can I move on from this? No, that's not what I wanted to happen. Dang it. Try that again. Sorry, so much little manipulations. Okay, so let's use CC stops to factor this expression. Okay, so what these expressions are called, or the method of factoring we're about to do, is called sums or differences of cubes. Okay, so kind of like with the difference of squares, there's some restrictions. There's only kind of one type of problem this works on. Okay, so there has to be two terms, and they both have to be perfect squares. Or sorry, perfect cubes. It does not have to be subtraction because there's a sum version of this and a difference version of this, a subtraction version and addition version. Okay, and they're very, very similar. There's really no using CC stops will work for both of them. Okay, so as long as it meets those two criteria, this is the method we can use. Okay, we've worked on cubes before. X cubed minus 5x squared plus 7x minus 35. Like that's something we would have factored by grouping. So just because it has a cube in it doesn't mean we're doing sums and differences of cubes. We would have factored that by grouping because it has 4 terms. Okay. So as long as it has 2 terms and both are perfect cubes, we can do this. So that's why I sent you guys that thing saying, hey, you should probably know some of your perfect cubes down 1 through 10. Okay? Do you know that 125 is a perfect cube? Do you know that 64 is a perfect cube? Okay? If you don't recognize it, it gets very hard to do this because again, it's very pattern based. Well, they both are. Okay. So what that is, dang, I should not have written that there. So how do I use CC stops? So whenever we factor one of these things, sum or difference of cubes, we always get a binomial times a trinomial. Yeah? Just like where we came from over here. Right? 2 terms times 3 terms, both times. Right? So I just kind of set up my shells, just like I did with the difference of squares. I set up my 2 little parentheses, and I worry about filling them in. Same thing here. I set up my parentheses, a binomial and a trinomial. So the first thing it says is cube root, cube root. So what that's referring to is that once you take the cube root of this, so what times itself 3 times will give you 64x cubed. Well, that would be 4x times 4x times 4x. So 4x goes there. It's always the same sign as the problem here. That's a minus sign. And then I need to cube root the 125. What times itself 3 times is 125. That's 5 times 5 times 5. So 5 goes there. So there's my CC. Right? Cube root, cube root. The SOPs does not deal with the original problem. I'm done with the original problem. The SOPs is all about that binomial. Okay? So I'm just going to focus on this now. Manipulate that. So SOPs square. So I'm going to take that first term of that binomial, okay, and I'm going to square it. Quite a few people say, when I say what's 4x squared, they're just like 4x squared. Okay, it's not what it means to square something. Okay, so be careful of that, right? 4x squared means 4x times 4x. So that's 16x squared. Opposite means the opposite sign. Okay. Product, take this times this. 4x times, I don't worry about the sign because I already dealt with the sign. 4x times 5, which is 20x. This last sign is always a plus. Always a plus. And then that last square, so I take that 5, right? I square it. Of course, 5 times 5. Yeah. Good job, Kylie. Who wrote down 10? 5 times 5 is 25. Okay. So we should be checking to see if this is right, okay? Or if we're done, I guess the other thing, right? Do I have anything in common? Nope. Anything in common? Nope. Any higher exponents? Nope. Any higher exponents? Yep. Ah, dang it. So is this still factorable? Okay. Well, there's three terms. We should be trying the AC method. I don't want you guys to write this down, okay? If I tried the AC method, A times C, which would be 16 times 25, would be 400, okay? I need factors of 400 that would add to 20. There are no factors of 400 that add to be 20, okay? This right here will always be prime, okay? The way these problems, where they come from, they never come from a trinomial that's still factorable, okay? Trinomials that are still factorable don't give us problems like this, so they'll never happen, okay? So you guys will not have to worry about ever trying to factor it. It's not because we're trying to give you simple problems. They just don't exist, okay? So that's the end of it. There's nothing else to do, okay? I'm going to clean this up just because there's so much going on here. So it's 4x minus 5 times 16x squared plus 20x plus 20. If we multiply that back together, it will get us where we started, okay? Again, we can quickly check that. Again, we're not going to check the whole thing. That would take forever, okay? But 4x times 16x squared. 4 times 16 is 64. X times x squared is x cubed. 64x cubed. The front works. Negative 5 times positive 25 is negative 125. The back works. There's a really good chance you got the middle right too. Okay? But you know the front and the back work. There's a really good chance the middle works. Okay? You can still mess it up, but at least you would have gotten most of it right. Okay? If you messed it up, it's because this one thing is wrong. That means you got 4 out of the 5 pieces right. That's pretty good. Okay? But we can see quickly that most of it's right. Okay? Let's try that again. So we look at our problem, see if it's fitting our criteria, right? 2 terms. Yep. Are they both perfect cubes? Is there a number times itself 3 times? That's 3. Nope. You're right, Audrey. Is there a number times itself 3 times? It's 81. Nope. Okay. Well, that one screwed it up already, right? Well, what are we forgetting about? Right? Always look for a GCF first. Forgot to do that. Right? That's the most basic step. Look for a GCF. Both of those have a 3 in them. 3 times 27 is 81. So we've taken out everything we can. There's nothing left in common, but is this still factorable? I still have a higher value exponent, which means there could be something that multiplies to be this. And it's not always, just like this. This wasn't factorable. There's a chance, right? Is there something I can try? Well, it's a cube, right? And is something times itself x cubed? Yeah, x times x times x. Something times itself 3 times 27? Yeah, 3 times 3 times 3. Okay, so these are perfect cubes. So that means I'm going to take my answer and keep going. That's 3 times. Now we're going to do a binomial times a trinomial. Okay, so a smaller set and then a bigger set. Okay. Now I'm looking here. I'm not looking at back to the original problem. Okay, I'm looking where I am now. I'm looking at this and saying, what would I cube root, or what would I cube in order to get x cubed? That's x times x times x. That's x. Same sign. And now look at the 27 and say, what multiplies by itself 3 times 327? 3 times 3 times 3. There's a 3 there. And then I'm done with the original problem. I'm not even looking at the original problem, that last problem. Now I'm just looking at the binomial that I just wrote. So we've done the CC. We did the cube root. Now we're on to the SOPs. S. S stood for square. I take that first term and I square it. X times x, of course, is x squared. O stands for opposite. take my opposite sign. P stands for product. I take these two things and I multiply them. I don't worry about the sign. X times 3 is 3x. Last sign is always plus. And my last term, I take that last term of a binomial, 3, and I square it again. S stands for square. 3 times 3 is 9. There it is, cleaned up. Again, we can check parts of it quickly to see if it makes sense. Okay, does our answer make sense, or is it junk? Okay, 3 times x is 3x times x squared is 3x cubed. That's where we started, 3x cubed. 3 times 3 is 9, times 3 is 81. And it was positive 81. There we go. There's a really good chance that the rest of it's right. Okay, but that took what, 5 seconds to check to see if most of it was right. Okay, so we can be pretty confident that our answer is right. Notice how there's always 2 pluses and 1 minus. 2 pluses and 1 minus. Just those first two can switch depending on what the sign of the original problem was. All right, started minus, switched, and it's always plus. Started plus, minus, always a plus. Okay? Always 2 pluses, 1 minus. Okay? I want you guys to try one on your own. Okay? Good. Anybody got anything? You get it again? Well, here's what I got.
Mr. Baker,
Yeah, Jake.
how do you type X like the squared on a keyboard?
Sure. I would do it like this. Use the Shift 6.
Oh, okay. Oh, I see. Okay. Thank you.
Yep. Worst comes to worst, you write X2. I hope that they understand. But make sure you're always looking for a GCF first, especially if you're not seeing those perfect cubes, right? You look at the last one there, 40 is not a perfect cube, and it doesn't even have a cube in it, right? It says x to the fourth. 135 is not a perfect cube, so you're always look for a GCF first. Once you take that out, see if there's more to do, right? That's again that kind of idea that there can be layers of factoring within a problem. We're going to start to see more of that, guys. Yeah, there's another worksheet you guys have on Google Class. Again, you don't need the worksheet, just need to write down the problems. I will be again doing that factoring seminar tomorrow morning. If you guys want to come in, do that with me. If you feel like you're struggling with factoring, want to get better faster at it, just understand a little bit better. Just like it's going to be a kind of a flow chart to help you guys make decisions about what to do. Because you do have, kind of like 5 different ways of factoring now. Like when do I do what? Okay, try to help you out with that. So.
Can you show me what 40x wait, I'm confused. I don't know how to say that, but
40x to the fourth.
yes, okay, perfect. Thank you.
We can always say it just like whatever power, like 40x to the fourth, or x to the third, or you don't have to say x squared. It could be x to the second power. You've just given special names to the 2 and the 3.
I almost said something like not like that at all.
I've heard plenty of like 40x4, like, and then I'm like, oh no.
I was about to say to the quad.
Oh, yeah. That makes sense. Yeah, we do talk about quadratics, which is unfortunate because I think quadratic and 4 for quad, but quadratic deals with the power of 2. So yeah, they've kind of I've seen some students get confused by that in the past, 2 versus the 4 sounds. So yeah, I think we're at the end of time. If you guys don't need anything, but again, there's like kind of 2 main ways I've seen people do this stuff. It's either off some mnemonic or just purely memorizing. So if this is something like you go and try and find a video for, I imagine most of the time it's just pure memorization. Like here's the pattern, fill in the chunks, and then you have to memorize the pattern. So